Imagine you're in a self-driving car. Suddenly, a deer leaps out. Ambulance sirens are wailing behind you. How does the car decide what to do? Brake hard, swerve, keep going.
Yeah, it's a super complex split-second thing, and it really gets to the heart of what we're diving into today. Artificial intelligence, but specifically looking at it through this idea of intelligent agents.
Right, so our mission today is taking the source material you've given us and really digging into what these intelligent agents are all about.
Exactly. We want to unpack what they are, how they, interact with the world around them, what actually makes an agent rational, and then look at the different ways we design them to be, well, smart.
We'll be analyzing the core ideas, connecting some dots, maybe challenging a few common assumptions people have about AI.
And hopefully revealing some interesting patterns along the way. You should definitely expect some aha moments about these sort of fundamental building blocks of AI.
Okay, so let's start with that foundational idea. What is an agent?
Well, at its simplest, an agent is just anything that can perceive its environment using sensors.
Like eyes or cameras?
Right, eyes, cameras, microphones, whatever. And then it acts upon that environment using actuators.
Hands, motors, wheels.
Exactly. Hands, motors, even software, writing a file or sending a network packet. It's a really broad definition, actually.
It covers humans, robots, software, pretty much anything that senses and acts.
And that definition immediately leads to this key concept, the percept sequence.
Okay, what's that?
So a percept is just what the agent senses at any single moment. The percept sequence is the entire history of everything it's ever sensed.
The whole history. Why is that so important?
Because what an agent decides to do now often depends critically on everything it's seen before, not just the immediate situation. Its past experiences shape its current actions.
Got it. So if that's the history, how do we think about what an agent should do versus what the actual program inside it does? Are they the same?
That's a crucial distinction. We talk about the agent function versus the agent program. The agent function is the abstract idea. It's the mathematical mapping from every single possible percept sequence to the action the agent should ideally take. The perfect plan, if you like.
Every possible sequence. That sounds huge.
Exactly. It's the theoretical what it should do. Now, the agent program is the actual code running on the machine, the practical implementation, the how it does it.
So why not just build the perfect plan?
Yeah.
Implement the agent function directly, maybe like a giant lookup table.
Well, that's the table-driven approach, and the sources are very clear. It's completely doomed for anything non-trivial.
Doomed? Why?
The size. They give this mind-blowing example of an automated taxi, just 1 hour of driving using maybe a camera feed.
Yeah.
The table mapping every possible visual history to an action would need more than 10 to the power of 600 million entries.
Wait, 10 to the what?
600 trillion zeros.
Right.
It is just staggeringly large.
Yeah.
Way, way more entries than atoms in the observable universe, which is only about 10 to the 80.
Wow. Okay, so yeah, doom seems about right. You can't build that table, you can't store it, you couldn't even design it.
Precisely. And that daunting size problem isn't just a technical hurdle. It fundamentally changed AI. It showed that intelligence couldn't just be about having a massive pre-programmed list of answers.
It forced a different approach.
Exactly. It revealed the real challenge. How do we write small, efficient programs that produce rational behavior instead of relying on these impossible tables? It shifted the focus to learning, generalization, and finding compact ways to represent knowledge.
Which leads us perfectly into this idea of rationality. What does it mean for an agent to be rational?
In AI terms, a rational agent is one that does the right thing. Simple enough, right? But what is the right thing?
Uh-oh. Sounds philosophical.
A little. AI generally takes a consequentialist view. We judge an agent by the consequences of its actions. Is the sequence of states it produces desirable?
And how do we measure desirable?
That's the job of the performance measure. It's a function that evaluates a sequence of environment states and gives it a score, basically. How good was the outcome?
Okay, but defining that measure seems tricky.
Yeah.
The sources mention the King Midas problem.
Yes. This is so important. If you get the performance measure wrong, you can get very unexpected, even counterproductive behavior.
Like the vacuum cleaner example.
Exactly. If you just reward it for picking up dirt, it might figure out that dumping dirt and then cleaning it up again maximizes its score.
Even though that completely defeats the purpose of having a clean floor.
Right. The real goal was a clean floor, maybe factoring in energy use or time. The performance measure has to capture the true objective, not just some easily measurable proxy. It's about carefully defining what success actually looks like.
It really makes you think about aligning AI goals with our actual intentions, which might be complex or have trade-offs like speed versus safety.
Absolutely. And this connects to another vital distinction. Rationality versus omniscience. They are not the same thing.
How's
An omniscient agent would know the actual outcome of its actions beforehand. It knows the future, which is, impossible.
Okay, so what's rationality then?
Rationality is about maximizing expected performance given the evidence the agent currently has from its percept sequence. It's about making the best decision based on what you know or can infer now.
The sources had that great example about crossing the street.
The Champs-Élysées example, yeah. You look both ways, see no cars, rationally decide to cross. If, unpredictably, a cargo door falls off a plane and hits you...
You weren't irrational,
No.
just incredibly unlucky.
Exactly, you couldn't have known. Rationality is about optimal decision-making under uncertainty, not about predicting the unpredictable. Perfection isn't the goal. Making the best possible choice with available information is.
So rational agents need to do more than just react. They need to gather information.
Yes, information gathering is key. Looking before you cross the street is an action taken to get more relevant percepts. Exploring an unknown area is gathering information.
And they also need to learn.
Critically important. A rational agent should learn as much as possible from its perceptions. Learning allows it to adapt, improve, and function effectively, even when its initial knowledge is incomplete or the environment changes.
This sounds like it connects to the idea of autonomy.
It does. An autonomous agent relies more on its own learned experience and perceptions rather than just being hard-coded with the designer's knowledge.
The sources mention some insects. The dung beetle.
Right, the dung beetle and the Sphex wasp. They have these seemingly complex, pre-programmed routines, but they're fragile.
Fragile how?
If you disrupt their routine in a way their programming doesn't anticipate, like moving the dung ball or the paralyzed caterpillar they plan to use, they just keep executing the old plan blindly. They fail completely because they can't adapt or learn from the unexpected situation.
They lack autonomy. They're stuck with their built-in assumptions.
Exactly. It raises a really interesting design question. What's the right balance between built-in knowledge and the ability to learn autonomously for creating robust AI?
Okay, so designing these agents. Since the giant table is out, how do we start? The sources introduce the PEAS framework, PEAS.
Yes, PEAS is super useful. It stands for Performance Measure, Environment, Actuators, and Sensors. It's a way to specify the task environment clearly before you start coding.
So for our automated taxi, the performance measure.
That would be things like make the trip safe, fast, legal, comfortable for the passenger, maximize profit, a combination of potentially competing factors. Roads, other cars, pedestrians, traffic signals, weather, road conditions, the whole context it operates in.
Actuators.
Steering wheel, accelerator, brake, turn signals, horn, maybe displaying messages.
And sensors.
Cameras, lidar, radar, GPS, speedometer, odometer, accelerometers, engine sensors, maybe a touchscreen interface for the passenger. Specifying all of PEAS gives you a really solid handle on the problem you're trying to solve. It defines the agent's world and its capabilities within it.
And once you have that PEAS description, the sources say the nature of the environment itself heavily influences the agent design needed. There are different dimensions.
Yeah, about 7 key dimensions they discuss, which really shape the challenge. First up, fully versus partially observable.
Does the agent's sensors give it access to the complete state of the environment relevant to its decision?
Right. A vacuum cleaner that only senses dirt right under it is partially observable. It doesn't know if there's dirt in the next room. A taxi can't see inside other drivers' heads to know their intentions.
And partial observability means the agent needs to keep track of the world internally, build a model.
Exactly. It needs an internal state to remember things it can't currently see.
Okay, next dimension.
Single agent versus multi-agent. Is it just the agent acting, or are there other agents whose actions affect outcomes?
Like chess versus a crossword puzzle.
Perfect examples.
Yep.
Chess is multi-agent and competitive. A crossword is single agent. Taxi driving is interesting because it's both cooperative, avoiding collisions, and competitive, vying for a parking spot or a fare.
And the sources mentioned randomization can be rational in competitive multi-agent settings.
Yeah, to avoid being predictable to your opponent, like in rock, paper, scissors.
Makes sense. What else?
Deterministic versus non-deterministic. If I take this action in this state, is the next state guaranteed or is there uncertainty?
Real-world traffic feels very non-deterministic.
Definitely. You can signal a lane change, but someone might subtly speed up or a tire could blow out. Dealing with that uncertainty, often using probabilities, is called being stochastic.
Okay. Then there's episodic versus sequential.
Right. Does the agent's experience break down into independent episodes where the action in one doesn't affect the next? Or is it sequential where decisions have long-term consequences?
Like spotting defects on an assembly line, each item is separate. That's episodic.
Yep, much simpler. Chess and taxi driving are highly sequential. Every move, every turn changes the future possibilities dramatically. Agents need to think ahead.
Got it. And static versus dynamic.
Yeah. Does the environment change while the agent is thinking or deliberating? A crossword puzzle just sits there static. Taxi driving is dynamic. The world keeps moving.
Even chess, if there's a clock, is kind of dynamic.
They call that semi-dynamic, yeah. The board state doesn't change on its own, but the conditions, time remaining, do.
Okay, two more. Discrete versus continuous.
Are the states, time, percepts, and actions distinct and finite, like chess squares and moves, or do they vary smoothly over ranges, like a taxi's speed, position, steering angle?
So chess is discrete, taxi driving is continuous.
Largely yes, though you might discretize some continuous aspects for planning.
And finally, known versus unknown environments.
This refers to whether the agent knows the rules of the environment, the laws of physics governing transitions and effects. Not the same as observability.
How so?
You can play solitaire, you know the rules, known environment, but you don't know which cards are where, partially observable. An unknown environment is like playing a brand new video game where you have to figure out how things work by experimenting.
Or maybe learning a specific passenger's preferences for music volume in the taxi.
That could be part of an unknown aspect of the environment, yes. And putting it all together, the sources say the really hard environments are partially observable, multi-agent, non-deterministic, sequential, dynamic, continuous, and unknown.
Like driving a rental car in a foreign country you've never been to.
That's a pretty good analogy, yeah. That captures most of those challenges.
So given all these environmental complexities, and knowing we can't use that impossible table, how do we actually build the agent programs? What are the architectures?
The sources lay out four main types, building in sophistication. The simplest are simple reflex agents.
Reflex, like a knee-jerk reaction.
Pretty much, they only react to the current percept. They ignore the entire history. They work based on simple condition action rules.
If-then rules, like if the vacuum sensor detects dirt, then turn on the suction.
Exactly, super simple. But the big limitation is they really only work well in fully observable environments.
What is that?
Because they have no memory. If the environment is partially observable, they can get confused or stuck. The taxi example. If it only sees brake lights right now, it might brake unnecessarily if those are just taillights slightly obscured. Or the vacuum agent without a location sensor might just go back and forth between two dirty spots forever.
An infinite loop.
Right. The sources mention that sometimes adding randomization can help simple reflex agents escape loops, but it's generally not seen as a rational approach in single-agent settings.
Okay, so how do we deal with partial observability?
That brings us to model-based reflex agents. These agents maintain an internal state.
A memory of the world.
Sort of. It's their best guess about the current state of the world, based on the percept history and their internal models how the world works.
So they need to know how the world changes.
Yes, they need a transition model. How the world evolves independent of the agent, and how the agent's own actions affect the world.
And how their sensors relate to the world state.
Right, a sensor model. How does the state of the world determine what the agent perceives? With these models, they can keep track of the parts of the world they can't currently see, much more capable.
But just knowing the state isn't always enough, right?
Yeah.
You need a destination.
Exactly. That leads to goal-based agents. These agents have explicit goal information descriptions of desirable situations.
Like be at the destination city or the floor is clean.
Precisely. They use their model of the world plus their goal to figure out sequences of actions that will achieve that goal. This often involves search and planning considering future possibilities.
So this is where thinking ahead really comes in.
Yes. Unlike reflex agents, goal-based agents explicitly consider the future. What happens if I do action A? Does that get me closer to my goal? It's much more flexible, too. Change the goal, tell the taxi a new destination, and the planning mechanism adapts. You don't have to rewrite lots of specific if-then rules.
Okay, but some goals might conflict, or some states might be better than others, even if they aren't the final goal.
Excellent point. That's where utility-based agents come in. They go beyond just goal, no goal.
How?
They use a utility function, which is essentially an internalized version of the performance measure. It assigns a numerical score, a utility, to any given state, representing how happy or desirable that state is for the agent.
So it's not just win-lose, it's how much you win or lose.
Exactly. Then the agent chooses the action that leads to the state with the highest expected utility. This is crucial for handling conflicting goals, like speed versus safety. How much risk is worth taking for a faster arrival?
And also for uncertainty, if you can't guarantee reaching a goal.
Yes, utility helps make rational decisions when outcomes are probabilistic. You choose the action that maximizes the average utility you expect to get. It's really the most general framework for rational decision-making we have.
And across all these types, learning can be added.
Absolutely. Any of these agent architectures can be enhanced with learning. Learning is what allows agents to overcome the limitations of their initial design, adapt to unknown environments, and generally become more competent over time. It combats that fragility we talked about.
So how does an agent learn? What are the components?
The sources describe four main parts. First, you have the performance element, which is basically the agent architecture we've just discussed, the part that actually chooses actions based on percepts.
Okay, the core agent.
Then there's the learning element. Its job is to modify the performance element to make it better.
How does it know what's better?
That's the role of the critic. The critic uses a fixed performance standard, like the overall goal or utility function, to evaluate how well the agent is doing and provides feedback to the learning element.
Feedback like, that move led to checkmate, that was good.
Exactly. The percept, checkmate, alone doesn't say if it was good or bad relative to the goal. The critic provides that evaluation. And crucially, that standard needs to be fixed and external, so the agent can't just decide, oh, losing is actually good now to make itself feel better.
Right. Avoid the Midas problem again. What's the fourth component?
The problem generator, this is interesting. It's responsible for suggesting actions that might lead to new experiences, even if they don't seem optimal right now.
Like exploring, taking a slightly different route.
Precisely. It encourages exploration over just exploitation of current knowledge. Like Galileo dropping rocks, the action wasn't useful in itself, but it generated data for learning. This exploration is vital for discovering potentially much better long-term strategies.
So the learning element uses feedback from the critic and new experiences from the problem generator to update the performance element, its internal models, rules, or utility function.
That's the essence of it, yes. It refines its knowledge based on experience.
Okay, one last major area the sources covered was how agents actually represent the world internally, how they think about it.
Right, the levels of representation. This gets into how expressive the agent's internal knowledge is. They described three main levels: atomic, factored, and structured.
It's atomic.
Simplest level. Each state is just a single indivisible thing, a black box, like state A or location B, useful for basic search algorithms where you just care about getting from one named state to another.
Okay. Factored.
Here, a state is described by a set of fixed attributes or variables, each with a value, like GPS coordinates, latitude, longitude, fuel level, current gear. This is common in constraint satisfaction problems or propositional logic. You can see relationships based on shared attribute values.
And structured.
This is the most expressive. It represents the world in terms of objects and their relationships. Not just coordinates, but there is a truck object ahead of me, and it has the property reversing, and it is related to a driveway object.
This sounds much more like how humans talk and think about the world.
It is. It allows for much richer descriptions and reasoning, using things like first-order logic or capturing the nuances of natural language.
But there must be a trade-off.
Definitely. Structured representations can be very concise, think rules of chess, versus listing every board state. But reasoning and learning with them becomes computationally much harder. Atomic is simple to reason with, but impossibly verbose for complex worlds. Factored is somewhere in between.
So real intelligent systems might need to use all levels.
Quite possibly, operating at different levels of abstraction simultaneously. The sources also briefly touched on how these representations might map to memory localist, where one concept maps to one node versus distributed, where a concept is spread across many nodes.
Distributed sounds more robust.
It can be, yeah. Damage to one part might just slightly alter the concept, making it more like a nearby idea rather than completely destroying it.
Wow. Okay, so we've covered a lot. From defining agents and environments to what rationality means, how environments shape design, the different agent architectures, the crucial role of learning.
And even how agents might represent their knowledge. It's really about understanding these core components: sensors, actuators, performance measures, models, goals, utility, learning to see how AI systems are built and why they function the way they do.
It definitely demystifies it a bit. It's not magic, it's complex engineering built on these principles.
Sophisticated design, learning, adaptation, trying to find efficient ways to solve problems in complex environments.
Which brings us back to that question the sources posed. Can AI do for general intelligent behavior what Newton did for square roots? Can we find those compact, elegant programs that capture intelligence, avoiding the impossible tables?
It's a powerful question, and it leads to a final thought for you, the listener. As these agents become more autonomous, learning and evolving based on their experiences,
How do we make absolutely sure that the purpose put into the machine is the purpose which we really desire? Especially when our own desires might be complex or change or even be things we haven't fully articulated ourselves.
it's a fundamental challenge. Ensuring alignment between increasingly powerful, adaptive AI and human values, that's arguably one of the biggest questions we face as we continue to build these intelligent systems. It's a deep dive into the very nature of the intelligence we're creating.